Welcome back to the Deep Dive, where we take your complex sources, strip out the noise, and deliver the core foundations and surprising insights you need fast. Today, we are focusing on something really foundational, the architecture required to make generative AI trustworthy and production-ready. We're moving past the hype about specific models and looking at how LLMs are transitioning from being these, novelties into complex autonomous systems.
Exactly. And when these systems start handling real workloads, running as software agents, coordinating across multiple data sources, making critical decisions, the challenges shift dramatically.
Right.
It's no longer just about tweaking the models with fine-tuning. The single biggest emerging hurdle is context engineering.
Okay, let's unpack that term because our sources highlight it as the key differentiator between a functional prototype and, well, a reliable enterprise system. What is context engineering, really?
In short, it's the systematic discipline of capturing, structuring, and rigorously governing all the information that exists outside the foundational models.
Probably external stuff.
All of it. This includes knowledge bases, short and long-term memory, external tools, and crucial human input. You're essentially creating the entire operating environment necessary to ensure the agent's reasoning is trustworthy and, consistently grounded in verifiable facts.
So it manages the full information journey from selection and retrieval all the way through.
To filtering and eventual refresh, exactly. If you don't master context engineering, your agent might be brilliant, but it's inherently unreliable.
That's the core vulnerability.
Yeah.
And look at what happens in current industrial practice, right? Most systems are relying on these ad hoc solutions.
Totally. Fragmented prompt engineering or RAG pipelines that are essentially just cobbled together. And these context artifacts are transient, they're opaque, and worst of all, they're completely unverifiable.
And what are the industrial consequences of that fragmentation? Because this isn't just about bad answers. This sounds like system decay over time.
Precisely. Our sources point to two major failures that stem from this lack of, systematic context governance. First, you get context rot.
Context rot.
Yeah, where the agent's long-term memory becomes stale or redundant and the system starts relying on obsolete facts. And second, knowledge drift, where the agent's understanding of its domain just sort of evolves without any traceable, verifiable reason. You can't audit or debug a system like that.
So this all suggests that we need a concrete architectural solution, not just another framework. What's the big aha moment from this research, the elegant solution that cuts through this fragmentation?
It's surprisingly simple, and actually it's deeply rooted in computer science history. An agentic file system, AFS abstraction.
Right.
Think of the classic Unix philosophy. Everything is a file. This abstraction provides a unified, persistent, and governed infrastructure that treats every piece of context, whether it's an API, a database, a memory, as a persistent, addressable resource within a virtual file system.
A file system for context. That concept immediately suggests order and structure. For you, the listener, our mission is to unpack how this foundational architectural shift transforms context management from a frantic, ad hoc scramble into a systematic, traceable, and ultimately a much more human-centered discipline. Let's start by looking at how this agentic file system actually operationalizes the concept of the LLM as operating system.
Well, the LLM as operating system has been a great metaphor, but the VFS, the virtual file system, is the concrete software architecture that makes it real. If the LLM is the kernel, then the agents and the human experts are the processes.
And those processes don't need all these complex custom interfaces. They just need to know how to perform standard, predictable file-style operations. Reading, writing, searching, executing. It simplifies the interface for everyone.
Dramatically, absolutely. And by imposing the structure of a file system, you instantly align Gen AI development with decades of accumulated wisdom and software engineering. This is how we make these systems production ready, how we make them auditable.
Let's break down the key engineering principles that the VFS operationalizes, because these are really the blueprint for the entire system structure. The first one is foundational. Abstraction.
Abstraction is the key to managing all that heterogeneity. Imagine your agent needs to retrieve information. It might need to hit a proprietary knowledge graph, check a real-time vector database, or query an external API like a weather service.
Right, three totally different things. That sounds like a maintenance nightmare.
It is, but the VFS projects all these wildly different sources into one uniform interface. The agent doesn't care if the data is a Neo4j graph or a Postgres table. It just sees a standardized path like context to a weather P, The complexity is hidden, it's abstracted away.
Which makes the agent's reasoning engine simpler and more focused.
Exactly.
Yeah.
And that abstraction leads directly to modularity and encapsulation, which is so crucial for
How
resilience.
so?
Well, each context resource, a memory store, a tool, is encapsulated as an independently manageable component. This means you can swap out backends seamlessly. If you decide to ditch one vector database for another, the change is isolated. It doesn't propagate throughout the agent's core logic.
I see the benefit for DevOps there, but I have to ask, aren't we just introducing a new management headache? If everything is a file, how do you stop the system from getting overwhelmed with millions of tiny, disorganized files?
That's where the structure is enforced and why the next two principles are so important. First, separation of concerns. We distinguish clearly between data and execution.
Okay.
So a non-executable file, like a customer profile, profile.json, is logically separate from an executable tool, like an analysis script, analyzer.py. This allows the agent and any human auditing it to correctly interpret intent. Is this data to be read, or is this code to be executed?
And that leads to the principle that has the most value for enterprise adoption: traceability and verifiability.
This is where the AFS really shines. Because every single interaction, reading a memory entry, writing a scratchpad note, invoking an API, is logged as a full transaction in a persistent repository.
Every single action.
Every one. This structured log, with all its metadata, provides complete context provenance. You can audit every step that led to an agent's decision. This is how you prove compliance. This is how you build trust.
And finally, that brings us to composability. If everything is uniformly structured, integration must get a lot easier.
It does. A consistent namespace and metadata schema let you dynamically combine context elements without writing custom code every time. The VFS provides the infrastructure where tools and knowledge can be mixed and matched with predictable results.
Now that we have this governed architectural foundation, we need to address the existential problem of the LLM, its memory. We touched on it, but let's dive into managing the lifecycle of persistent context. We know LLMs are fundamentally stateless.
That's the key operational challenge, right? Once the inference call finishes, the LLM's memory of that session just vanishes. So to sustain any kind of coherent long-term interaction, you must have an external persistent context repository.
And the AFS unifies this repository by layering context management into 3 distinct components.
That's right. 3 governed components.
Okay, so let's follow a piece of information as it travels through this system. We start with the ultimate source of truth: history.
History is the immutable record. It captures all the raw interactions, user inputs, system outputs, intermediate reasoning steps as they happen. It's logged globally and permanently, time-stamped, and tied to the originating agent. Think of it as a fully transparent judicial archive.
So it's strictly read-only and provides the ultimate audit trail.
Exactly. It's the ground truth.
So history is the raw transcript. The next layer, memory, is where that raw information is refined and made useful for the agent.
Correct. Memory is derived from history through transformation processes like summarization, embedding, indexing, things like that. It's optimized for fast retrieval by the agent. And unlike history, memory is typically persistent, structured, and, well, it's mutable. It can be refined and improved over time.
And the research shows this isn't just one big chunk of stuff. The VFS manages different types of memory that are essential for high-level performance.
It has to, because different tasks require different kinds of context. The system manages temporal memory, like short-term scratch pads, and medium-term episodic memory, which are session summaries. Then you have long-term memory, like fact memory, atomic facts, procedural memory, the definitions of all the tools, and user memory.
Which would be profiles, preferences, that sort of thing.
Exactly. And by exposing all these different types through a single namespace like context memory agent-type episodic, the agent knows exactly what kind of knowledge it's accessing.
Precisely. And that brings us to the third component, the scratch pad. This is the working memory. The scratch pad is the temporary task scope workspace, right?
Yes, often mounted like context pad task ED. It's ephemeral. This is where agents store temporary hypotheses or drafts or partial computations. Once the task is done, the AFS governance rules take over. Relevant artifacts from the scratch pad are integrated into long-term memory or archived in history, and the temporary pad is automatically pruned.
So the VFS isn't just organizing, it's actively governing the data lifecycle versioning, pruning, logging state transitions. This keeps the whole repository scalable and critically auditable.
It turns memory management from a bunch of brittle custom scripts into a robust, policy-driven system.
This robust infrastructure leads us directly to the operational layer, the context engineering pipeline. Now we need to discuss how this persistent knowledge actually gets injected into the LLM during runtime, a process that is, well, brutally constrained by the models themselves.
The pipeline is functionally mandated by 3 unique architectural constraints that GenAI introduces. These constraints are why traditional software solutions just won't work here.
Constraint 1, the famous one, the token window constraint.
This is the hard limit on active context. Even with massive Windows 128K, 200K tokens, that capacity is finite. And when you factor in the rising computational cost as that context length increases, the system can't just dump all relevant knowledge. It has to be ruthlessly efficient.
So the pipeline has to perform complex curation, compression, even incremental streaming.
It has to. It's not just a limit. It's a computational bottleneck we have to optimize around.
Right.
Constraint 2 is the statelessness we just discussed. Since the LLM forgets everything, external persistence is non-negotiable. But by persisting everything, you introduce the problem of redundancy and unchecked memory growth. The pipeline has to actively manage that.
Okay, and constraint 3, the one that makes system validation so difficult, non-determinism.
Right. Since LLMs are probabilistic, the exact same prompt can give you slightly different outputs. This makes auditing and testing incredibly difficult in a traditional software sense. So the pipeline has to preserve every input-output pair, along with all the metadata in the file system to enable audit, testing, and crucially, the replay of the agent's reasoning.
These constraints necessitate the 3-part context engineering pipeline. This is the operational layer. Let's start with the first step, the context constructor.
The constructor is the brain of the retrieval process. It's the gatekeeper. It selects and prioritizes context from all the VFS mount points, memories, tools, knowledge bases, and it manages that constant trade-off between giving complete information and respecting the token limit.
And how does it ensure traceability before the agent even starts reasoning?
This is critical. The constructor enforces governance constraints like privacy first. Then it outputs a JSON-formatted manifest. This manifest records exactly which context elements were selected, their source path in the VFS, and why they were chosen. It's the transparency artifact.
Okay, moving on to component 2, the context updater. This manages the physical transfer of that context.
For simple single-turn tasks, the updater might just feed a static snapshot into the model. But for complex, long-running sessions, it performs incremental streaming. It's dynamic. It continuously monitors context size and relevance, proactively swapping out older fragments with fresh material as the dialogue evolves.
So the agent doesn't lose the thread halfway through a complex task.
Yeah, exactly. And finally, the mechanism that closes the loop, the context evaluator.
This is the validation stage.
It is. Its job is to verify the model outputs against the source context, the manifest, the memory, the history, to detect factual inconsistencies or, hallucinations. It generates high-level metrics like confidence scores and records those back into the file system as metadata.
And this final stage is where the human becomes absolutely integral, right? It's not just automated checking.
Correct. The human in the loop is critical here. When the system detects low confidence or when an output conflicts with its own memory, it triggers human review. The resulting human annotations, domain corrections, tacit knowledge are then explicitly captured and stored as first-class context elements, maybe in a path like context human.
You are systematically turning tacit domain knowledge into verifiable explicit system context. That's a huge shift. Okay, let's ground this powerful architecture with some real-world examples from the Agentic framework, which actually implements this agentic file system.
Right. The Agentic framework supports various LLMs and external services via a unified protocol, the MCP, and the central mechanism for agent action is the function.
These are the executable files, the tools that the agent delegates tasks to.
Exactly. They are modular components, a Python script, a Node.js module package with metadata describing what they do. This lets the agent autonomously discover and invoke them. The VFS just makes them addressable.
So let's look at the 2 exemplar use cases that show the practical value of the AFS. First up, memory persistence.
In Agentic, making an agent that attains memory is declarative, not procedural. You just specify a storage location in the AFS namespace, say, a SQLite database file path. The VFS then automatically manages all the complex mechanics, persisting the history, retrieving relevant memory, injecting it into the constructor.
So the developer doesn't have to manually manage state synchronization. The file system does the heavy lifting.
That's it. And the second example, external tools and the model context protocol. This is how a complex external service becomes a simple file.
Okay.
Let's say you have an external service that manages your corporate communication logs. You mount that service as an AFS module, for example, at modules log MZP. The agent then interacts with it using standard file system commands. Instead of writing complex API handlers, the agent just executes AppSec on a path like module slog MCP search user tickets.
The AFS handles the entire API abstraction.
The whole thing. It makes external services first-class citizens in the agent's environment.
So if we take a step back and summarize, what's the ultimate value of adopting this agentic file system abstraction? What's the big payoff here?
The payoff is operational maturity. This architecture provides a concrete substrate for that LLM as-OS paradigm, enabling governance that was, frankly, impossible before. We are moving GenAI development beyond ad hoc prompt management
And brittle RAG pipelines.
and brittle RGI. By treating context as managed, versioned, and auditable files, you can finally apply mature DevOps and data ops practices, versioning, reliable deployment, automated testing to the context layer.
It sounds like we are shifting from building these unreliable black boxes toward creating verifiable, scalable software systems.
That's the entire point, and the research points to a fascinating, even slightly provocative future direction that builds on this, something for you to mull over.
Okay, here's where the architecture starts to feel truly alive. What's the final thought?
Well, currently, the context constructor selects and streams context to the agent. Future extensions detailed in the sources aim to enable agentic navigation within the AFS hierarchy itself.
Meaning what exactly?
This means agents will autonomously browse, organize, and even restructure their own mounted data, memory, and tools based on their experience. If an agent can independently browse and modify its own verifiable knowledge structure, the file system ceases to be just infrastructure. It becomes a living knowledge fabric that co-evolves with the agent itself.
An auditable system that organizes and improves its own brain. That is a massive leap forward. Thank you for diving deep with us into the architecture of tomorrow's AI systems. We'll see you next time.